All right, welcome back. And now we're going to talk about linear modeling in this section 9B as in boy. And so let's jump right in. So now that we've covered functions, what they are and how to set them up, let's talk about linear modeling. Now, a linear function has a constant rate of change and a straight line graph. Okay, so we're all familiar with the linear functions. They're just straight lines. The rate of change is equal to the slope of the graph. The greater the rate of change, the steeper the slope. Calculate the rate of change by finding the slope between any 2 points on the graph, and we calculate the difference in the y direction and the difference in the x direction, and we divide the two. So it's always rise over run. So it's change in y divided by change in x. Change in the dependent variable divided by the change in the independent variable. To find the slope of a straight line, look at any 2 points and divide the change in the dependent variable by the change in the independent variable. Again, just repeating what I just said. So notice here we pick 2 points. So all we have to do is calculate the distance from this point all the way over here to this point in the the horizontal direction. So in the x direction. Then we also measure the distance from point 2 down to point 1, or up from point 1 to point 2 in the vertical direction, right? So this would be our change in y, or what we call delta y. Delta just means change in. And then of course this would be our change in x. Okay, and so we would just divide delta y divided by delta x. Okay, or rise over run. All right, so let's look at this example. It says a small store sells fresh pineapples. Based on data for pineapples prices between $2 and $5, the store owner created a model in which a linear function is used to describe how the demand, the number of pineapples sold per day, varies with the price. For example, the point $2, 80 pineapples means that at a price of $2 per pineapple, 80 pineapples can be sold on an average day. What is the rate of change for this function? Discuss the validity of the model. Okay, so we're going to look at the 2 points. We're going to figure it out. So if we look at point 1 and point 2, so we're going to find the slope, right? All we have to do is take point 2, right? And we're going to take the change in the dependent variable, so right here. And so we'll do 50 minus 80 divided by the change in the independent variable. And we'll do 5 minus 2. And so we get a difference of what? We get negative 30 pineapples over what? $3. And so we get what? Negative 10 pineapples per dollar. All right. And so that would be the rate of change, right? So what this is telling us is that for every dollar you increase the price of the pineapples, you're going to lose on average 10 pineapples sales per day. Okay. And so that's what the rate of change tells us. Now, the rate of change rule allows us to calculate the change in the dependent variable from the change that we see in the independent variable. So here's the change in the dependent variable. This is how we calculate it. So we find the rate of change. So we just did that. And then we multiply that by the change that we see in the independent variable. So we know how to find the slope, the rate of change here. And then if we know the change in the independent variable, we can multiply these two quantities to get the change in the dependent variable. Okay, so we want to use this to find what would be the change in the demand of pineapples if the price increases $3, right? Well, we know that the rate of change is negative 10 pineapples per dollar. So that's our change. And then we're going to increase by $3. So that's the change in the independent variable. And so if we multiply these together, we'll notice that dollars are going to cancel with dollars and we end up with pineapples. So we just multiply across the top and we get what? Negative 30 pineapples, which makes sense, right? Based on what we just discussed. So we're going to lose, on average, 30 pineapples per day in sales. Okay, so again, the independent variable is the price of the pineapples. Dependent variable is the demand for the pineapples. That's the sales. And then the rate of change in the demand with respect to price is negative 10 pineapples per dollar. And then the change in the demand, so here's our function, our formula, equals the rate of change times the change in the price. And so we get negative 30 pineapples. Now, the general equation of a linear function is given by this. The dependent variable is equal to the initial value plus the rate of change multiplied by the independent variable. Okay, so now we're putting it all together to form the general equation of a linear function. So the algebraic equation of line, we use x commonly for the independent variable, like I said before, and y is used for the dependent variable. And slope, we denote slope using m, and then we use the y-intercept as b. Okay, so b is the initial value in this case, that's the y-intercept. Okay, m is the rate of change, that's the slope. And then of course the independent variable is x, and the dependent variable is y. And when we put it all together, we get the commonly used equation of a line, y equals mx plus b. All right. So now let's look at this one. So for example, the equation y equals 4x minus 4 represents a straight line with a slope of 4. You can see that it's the m, right? So the slope always goes with the independent variable. It's always multiplied by the independent variable. And then the intercept is always what's added or subtracted, right? So again, remember, it's y equals mx plus b. So it's always plus. So this would be a negative 4, which tells us that the y-intercept is negative 4, not positive 4, okay? And that tells us where the graph is going to cross the y-axis. That's the y-intercept, okay? And so the y-intercept is negative 4. The point of the y-intercept is going to be 0, negative 4. Okay, now slope. Remember that we said before that the slope is related to the steepness of the line, the graph. So the larger the larger positive slope, the steeper it is going left to right, as you can see in this case here. but the slope can be also large negative. So the larger it is negative, the steeper the slope is, but going the other direction. So it goes down from left to right. Okay, so negative slopes go down from left to right. Positive slopes go up from left to right. And the larger the value, the steeper the slope, either negative or positive. A slope of 0, by the way, is the horizontal line. Okay, now, if we have lines that have the same slope, but have different y-intercepts, then we have parallel lines, but they intersect the y-axis at different locations, as in the picture we see here. Okay? So lines that have different intercepts but the same slope are parallel lines. All right, so now in this case here, we're going to use the function shown to write the equation of a line that describes the rain depth at any time after the storm begins. So x represents the number of hours after the storm has started. Okay, so use the equation to find the rain depth 4 hours after the storm began. So the first thing we want to do is we want to find the slope. And so you can see here in the diagram that they took 2 points, right? It doesn't matter, any 2 points. And it shows that, for example, from 0 to 1, it shows the same thing. So 0.5. So it goes over 1 hour and up half an inch. So for every hour, it goes up half an inch. So again, the slope is the change in the y, which is in this case rain depth, divided by the change in the x, which is time in hours. So this tells us that it rises, the slope is telling us that the rain goes up half an inch every hour. Okay, so the slope is 0.5 or a half. Okay, also the y-intercept is at the origin at 0, right? Because that's at 0 hours, we have 0 rain because, again, that's when the rain just starts. Okay, so in this case here, y equals mx plus b, where m is equal to a half and b is equal to 0. So that gives us y equals 1/2 x. And so if x is 4, then y equals half of 4, which is going to give us 2 inches. So after 4 hours, based on this model, there are 2 inches of rain. All right, now, creating a linear function from 2 data points. The first thing we have to do is we have to let x be the independent variable and y be the dependent variable. Find the change in each variable between the 2 given points and use these 2 changes to calculate the slope of the line, or the rate of change. So the first step is finding the slope. Okay. Now, once you find the slope, then you're going to substitute in the m for the slope and the numerical values for one of the 2 points. Usually use one of the 2 points, but use the point that gives you the simpler, not the simpler answer, but gives you the easiest way to calculate the intercept. Because that's the thing we want to do. We want to plug in one of the 2 points. It doesn't matter which point we use. And then we solve for b, the y-intercept. And then once we find both the slope and the y-intercept, we use those 2 to write the equation of line, which, by the way, is called the slope-intercept form of a line, because all you need to know is the slope and the y-intercept. All right. All right, so let's look at oil use. Okay, Until about 1850, humans used so little crude oil that we can just call the amount zero, at least in comparison to the amount used since that time. By 1960, humans had used a total cumulative amount of 600 billion cubic meters of oil. Create a linear model that describes world oil use since 1850. Discuss the validity of the model. All right. Okay, so in 1850, we're going to start that at time zero. So at that point, we're assuming that the crude oil used was zero, and that's going to be from that point to 1960. I guess that's when they started using more, and that's when we're going to start measuring. Okay, so then in 1960, we have 600 billion cubic meters of oil that had been used. Okay, so here are data points. In 1850, we had zero. In 1960, we had 600 billion. So the magnitude is in billions of cubic meters. Okay, so now we're going to use these two data points to find our slope. Okay, so again, make sure you do rise over run. Difference in the y's divided by the difference in the x's. Okay, so, and again, make sure you subtract in the same direction. So here we have 600 minus 0. So we're going to do the same thing on the top. We're going to do 1960 minus 1850. Okay, so however you subtract on the top, you must do the same in this like manner in the bottom, else you get the wrong sign. Okay, so now this tells us that the rate of change is 5.45 billion cubic meters of oil per year. That's how it's been growing based on these two data points. Now we're going to use one of the 2 points. Now here's the thing. I would use this one because it has a 0 in it, which is going to make our calculations much easier. Okay, so use the first data point, 1850, 0. And then we're going to plug that in to our equation to find the y-intercept. Okay, and so when we calculate this, we get negative 10,083 billion cubic meters of oil per year as our y-intercept. Okay, now immediately in this context, now that is the y-intercept, but you always ask yourself, does it make sense in the context of the problem? Now here it does not make sense because we can't have negative usage of oil, right? So back the y-intercept, right? So that wouldn't make any sense to have a negative y-intercept. But in any case, our final equation for this problem, this would be our equation of a line. But then again, we would also recognize that in this case anyway, the y-intercept is meaningless. Okay, so here's a couple things. Validity as a model for oil consumption. Draw the graph only 4 years after 1850, right? Because anything before 1850 is beyond the domain. So years prior to 1850, which we assumed oil consumption to be 0, are not in the domain of the function, so we wouldn't even consider that. So again, the y-intercept is meaningless in this case. The more significant issue is whether the rise in oil consumption has been linear. Okay, so the question is the model really linear or is it something else like exponential? So the rate of oil consumption tends to increase with population. So in fact, it has increased more rapidly than population because the average person uses more oil now than in the past. Okay, so it makes more sense that the rate of consumption is going to probably follow a more of a exponential. All right. All right, so there we go. And again, if you have any questions, please make sure you reach out and get some help from either myself or the tutoring center. Use the tools available to you on My Math Lab. And again, email me as well. I'll help you as best I can. And you enjoy the rest of your day.